In this video, we'll talk about another type of question that can be asked with regards to area between two curves, and that's finding the region bounded by two curves. So the main difference here between an area between two curves question and a region bounded by two curves question is for this question, you're generally not given what the bounds of the integration should be, where you should start and stop the integration. And to sort of motivate this, let's draw a picture of what this might look like and see how we can figure out how we would solve this problem. So a region bounded by two curves might look something like this. So there's, say, my two curves, it's two parabolas. Any curves would work in this case. And I want to find the area of the region bounded by these two curves. Well, what region is that for this picture? Well, it's the part that's trapped between the two curves. So it's just this part here in the middle. So how are we going to find that area? Well, this looks like an area between two curves where I just start at this point and end at this point. And how do I know where those two points are? Well, I find them by looking for intersections of these two curves. So the process here for finding the region bounded by two curves has these sort of steps. So first, you want to find intersection points to figure out where these curves cross. Secondly, you have to figure out which function is on top in the region between those two intersection points, right? Because these curves cross, one function is not always on top of the other one. But what I care about is which one's on top in the region that I'm actually looking to find this area here. And that can be done by plugging in some points in between those two crossing points. And then from there, you can just work out the integral like you would normally, because now you know which function's on top and where to start and stop the integration. That's how these problems all work. Let's see one example of working all this out for a certain problem. So find the area of the region bounded by the graphs of y equals x squared plus 2 and y equals 3x plus 6. So based on these two shapes, right, this is a parabola facing upwards and this is a straight line, we should have the parabola on the bottom and the line on top because that's the only way you're going to get a bounded region, right? Something like here's a parabola, here's a straight line. The line being on top of the parabola is the only way that I get a bounded region here because the parabola is facing upwards. So let's set these equal, figure out where they intersect, and see if we actually do get that result here. So to find intersection points, I want to set those two equations equal to each other. So I want to set x squared plus 2 equal to 3x plus 6, and then solve out. So by moving terms to the other side, x squared minus 3x minus 4 equals 0. This factors as x minus 4, x plus 1. So my intersection points are at x equals 4 and x equals minus 1. So those should be my bounds of integration. Now to check which function's on top, I just have to plug in one point between 4 and minus 1 to figure out which one's bigger. So let's plug in 0. If I plug in 0, I see that my parabola is at 2, my straight line's at 6, therefore the straight line is on top. This is my top function, and this is my bottom function. Now we can just do the integral like we normally would, given these bounds of integration and those two functions knowing who's on top and who's on the bottom. Let's work it out. I then get the integral from minus 1 to 4 of the top function, which is the straight line, minus the bottom function, which is the parabola, dx. Now we just work out the details. 3x plus 4 minus x squared dx. And if you notice, this expression here is the same as we had for the expression up here, with a minus sign potentially depending which one's the top and which one's the bottom, but it's the same expressions you get there, and that will generally always be the case for these sorts of problems. Integrate this to get our antiderivative, and then plug in the endpoints. X squared is 16, so that's 48 over 2 plus 16 minus 64 thirds minus a 3/2 minus 4 plus 1/3, because the negative 1 cubes is negative 1. I get a 24, I get a 16. That minus 64 gives me a minus 65 over 3 plus a 4 and minus a 3/2. It's going to come out to 125 over 6. So that's the general process of how you can use this idea of area between two curves to find the area of a region bounded by two curves. You just have to find the endpoints first by looking for intersection points, and you can go from there using your normal methods to find the area of that region as well.